Right, so now let's try the May June 2021 5 points. Question number 2, the analysis and evaluation question. Right, okay, so a student investigates the collision of two gliders A and B on a linear air track. Okay, a card is attached to glider B. Okay. Glider B has mass capital M. A mass M is added to glider B. Okay. Glider A travels at a constant velocity u towards the stationary glider B. Okay, the gliders then collide and move together towards the light gate. Okay, the card passes through the light gate, which is connected to a data logger. Okay, the student records the velocity of two gliders from the data logger. Okay, student changes the mass and repeats the experiment. It is suggested that V and M are related by the equation AU M plus M plus AV. Okay, so just to make sure, uh, what do we have? A is the mass of glider A. U is the initial velocity of A. Okay. Okay. So M plus A V. So this is like the principle of conservation momentum equation. Okay. A graph is plotted of 1 over V on the y-axis against M plus M on the x-axis. Determine the expressions for the gradient and the y-intercept. Right. So 1 over V. Okay, so when we take 1 over V on this side, okay, so when we take 1 over V on this side, so what do we get? So let's see. So 1 over V equals to M plus A and U. This is supposed to be on the x-axis, right? So let's expand this. So M plus M, let's say divided by AU, plus A divided by AU. So A and A get cancelled over here, and this we can take it out. So we are left with M plus M, 1 over AU plus, 1 over AU plus 1 over U. So gradient is 1 over AU, and y-intercept is 1 over U. Right, just to make sure that we have the correct thing, we simply just cross multiply. Then we separated the fractions, cancel the A, and then M plus M. Okay, all right. Values of M and V are given in the table 2.1. The value of M is 330 grams per 5%, okay, plus minus 5%. Each value of M has a percentage uncertainty of 5%. Okay, so that means the right. Okay, what do we have over here? So M plus M. Okay, each value of M has a percentage uncertainty of plus minus 5%. Okay, calculate and record the values of M plus M per gram and 1 over V per second centimeter. Okay, second per centimeter. Okay. So M plus M. So we are going to add 330 with all of them. So 330 plus 50. Right. Okay. 380. We'll deal with the uncertainty later on. So 50, 150, 480. Then we have 250, 580. Then we have 350, 680. Then we have 500, 830. And then 600, 930. Okay. Now 1 over v will come back for the uncertainties later on. So 1 divided by 4.42, 0.2262. I'm just recording the raw values, and then we will later on come to the uncertainties, and then we'll figure out how many decimal places or significant figures we need. So 3.92, we get 0.2551. Okay. Then we have 3.40, 0.2941. 3.02, 0.3311, 2.58, 0.3876, and then 2.33, 0.4292. Okay, all right. Okay, now coming to the absolute uncertainties for this. Now, for the uncertainties for the M and M, notice that we don't need the percentage uncertainties. We need the absolute uncertainties. So this means that for the absolute uncertainties, what we will have to do, M plus M uh, equals to 5% times by, sorry, 5% of M. Okay, so they've given us the, percentage uncertainties, right? So we need to come up with a way to, find out the absolute uncertainty. So we know, sorry, no, not over here. We know that when we add or subtract quantities, their uncertainties add up. So they're plus minus delta m plus delta small m. Okay, so to figure out this, we need to have delta m over m. They've given us that this is 5%. So we will just add them up, right? Delta m will be 5% of m, capital M, capital M. This would be the same for small m also, identical. So this means that we are just multiplying 5% with the percentage, and sorry, we're just multiplying 5% with m plus m actually. So when you add small m, you'll have 5% also. So delta small m would also be 5% of small. So when you add these up, you'll just doing 5% of m plus m. So 5% of these values basically. So 5% of 380, oh sorry, 19. Okay. Absolute uncertainty has to be given in one significant figure, so we'll convert this into 20. Then we have 440, 480, 24, so again 20. Then 580, 29, 30, 680, 34, 30. Now 830, oh sorry, no, 40 and 930. We get 46.5, so roughly around 50. So absolute uncertainty is always in one significant figure. Okay, all right. So if we look at it, how many decimal places do we need for 1 over v. So 3 decimal places are more than enough over here. So we can, delete the fourth one. So 1, 1, cancel, cancel. This becomes 8, but this remains as it is. Okay, right. Plot a graph of 1 over v against m plus m per graph. Include the error bars for m plus m. Okay, all right. Let's do this. I'm going to do this. I'm going to pause and do this, and then I'm going to come back because this might take some time. Okay, so I have plotted the worst fit and the best fit. So the worst fit over here has the steepest gradient. However, we need to make sure that the line should always pass through the error bars. And the best fit should be closest to most of the points at least. So this is my sketch over here. All right, so going back over here, so remember the m plus m was on the x-axis, so the error bars will also be horizontal. All right. So determine the gradient of the line of the best fit. Include the absolute uncertainty in your answer. So basically, we need both of the gradients, right? So let's choose the points that we see very clearly on this, both of the lines. Let's say for the best fit I have found, I'll mark it with green, the light green. This point over here, and for the worst fit I'm choosing this one. I'll come back to identify. And another point we need for those, they're roughly crossing over at the same point over here. However, let's keep searching. They are okay, so my best fit is crossing over here. My worst fit, uh, let's pick another point. Okay, found it. All right. Okay, so let's find out what those points are. So this point for the best fit, this is at 8, 20, and 0.38. Okay, so let's write over here 820, 0.38. This point is going to be, I think, 750 or wait, yeah, 750 and 0.37. Okay, right now about this point is at right 580 and 0.30. And for the best fit line, this was 370 and 0.22. Right, okay. Sorry, let's label this. Right, okay. Now we go to our, right, for the gradient of best fit, grade we had, sorry, again, 0.38 and 0.22. and the points were 820 and 370. Okay, now the gradient of worst fit 0.37 to 0.30 and 750 to 580. Okay, let's calculate them. So we have 0.38 minus 0.22 divided by 820 minus 370. We get 3.556 10 raised to the power minus 4. And for this one, wait, this was in centimeters. Okay, all right. And then we have 0.37 minus 0.30 divided by 750 minus 580. This is going to be 4.118 10 raised to the power minus 4. So we need to find out the uncertainty in the gradient. So gradient of worst fit minus the gradient of best fit, we will get 4.118 minus 3.556, we get 0.562. All right, so again, absolute uncertainty, we need to just convert it into 0.6. Wait, sorry, 0.6. And this is going to be just 3.6 plus minus. Both of them times with 10 raised to power 4. Okay, so one significant over here and one decimal place that corresponds to that, right? Right, okay. Now we move on. Determine the y-intercept of the line with the best fit. Include the absolute uncertainty in your answer. Okay. So for the y-intercept, we need to consider the y is equal to mx plus c. Right, y is equal to mx plus c. We chose one of the points on our best fit to be 820 and 0.38. Right. So what are we going to do? Right, okay. Sorry, we found the gradient of the best fit line to be 3.556 10 raised to power minus 4, or just 3.6. So y 0.38, 3.6 10 raised to power minus 4, x was 820 plus c. So c is going to be the difference of those minus 820 times by 3.6 times by 10 raised to power minus 4. So we get 0.0848. Okay. And 1 point from the, let's say 753, 0.37. Okay, so this was for the best fit. This was from the best fit. Okay. Now to get the uncertainty, we need the worst fit. One of the points that we took was 750, 0.37. Right, so we will do the same process again. C is equal to 0.37 minus Now the gradient of the worst fit, that is going to be 4.2, 10 raised to power 4 times by 750. So 0.37 minus 4.2 times by 10 raised to power minus 4 times by 750. We get 0.05, sorry, 0.55. So the uncertainty in C would be just 0.0848 minus 0.055. So 0.0848 minus 0.055. So this comes out to be 0.02 or roughly 0.03 plus minus. Now we are going to take the best fit up to 2 decimal places, 0.08. Right, okay. Using your answers to A, C3, and C4, determine the values of A, U, and A. Okay. So we said that the gradient was 1 over, wait. A, U, and y-intercept was 1 over U. Okay. One over U. So gradient we found out for the best fit, that was 3.6 10 raised to power minus 4 equals to 1 over AU, and the AU is going to be 0.08 is equal to 1. So that means U is equal to 1 divided by 0.08, 12.5. Okay, so, and that means that A is going to be 1 over 12.5, 3.6, 10 raised to power minus 4. So 1 divided by answer times by 3.6, 10 raised to power minus 4. So we get 222.2. Right, so we need to round it up to some appropriate significant figures. So let's not go beyond two significant figures. So for A, we will write, let's say, 220. A was the mass in in grams. Wait. Yes, A was the mass, and since we were doing it in grams, that will be in also grams, because obviously grams can be added with grams. Grams cannot be added with kgs as they are. One of them has to be converted into the other units. Right, so A is in grams, and U is 12.5, so I'll just roughly write it as 13 meters per second. Oh no, sorry, centimeter per second. Because the speed that we were going for was actually centimeter per second. So that's going to be in centimeter per second. Right? Because all of the calculations we're doing is in grams, mass is we're taking in grams, velocity is we're taking in centimeters per second. This is how we have actually drawn our graphs also. Okay, so the same units are carrying forward up to over here. Now, the percentage uncertainty in A. Okay, so percentage uncertainty in A was actually coming from the gradient. and the y-intercept. Okay, so percentage uncertainty in A is coming from percentage uncertainty in gradient and the percentage uncertainty in y-intercept. So delta u over u times by 100%. So because we actually calculated A to be reciprocal of the product between gradient and u, so that's how we'll find out the percentage uncertainty. So the percentage uncertainty in the gradient that, wait, we did calculate this. 0.6, 10, so the power doesn't change the percentage uncertainty, so we will just write 0.6 over 3.6. Plus y-intercept uncertainty was 0.03 to 0.08%. So 0.6 divided by 3.6 plus 0.03 divided by 0.08. Then times by 100, we get 54.1, roughly about 54%. Okay. Now, the experiment is repeated. Determine the value of m that would give the velocity of, give a velocity v of 2 centimeter per second. Okay. Okay, now we can use our model now. Okay. So model was, going back, this was the model. We need the mass m, right? So AU over V, so AU over V is equal to m plus a. Okay, so AU over V m plus n plus a. Okay, so I'll just copy this, actually cut this, and paste it over here. Okay, so u was 13, we calculated u to be 13. Okay, right. So mass would be, oh, sorry, no. So mass could be, let's make m the subject. That would be AU over V minus capital M minus A. So now we can plug in the values. So appropriate mass M would be A was 220 grams, U we figured out to be 13, divided by V, V is 2, minus M is capital M. Wait, capital M, did we know capital M? Oh, yes, 330 grams, okay. And A, again, we calculated it out to be 220. Okay, so now 220 times by 13 divided by 2 minus 330 minus 220. So we get 880. So 880 grams. All right, and that's about it with our model over here. Oh, sorry, this analysis question over here. All right, so see you in the next question. Okay, so let's try the May June 2021's 5.2 variant. Previously we did 5.1/5.3. All right. A student investigates the current in a circuit containing a cell as shown in figure 2.1. Student connect two resistors of resistances R and R2 between P and Q. The ammeter measures the current I. Okay, the student repeats the experiment with different resistors between P and Q. It is suggested that R1 and R2 are related by the equation this, where E is the electromotive force EMF and small r is the internal resistance of the cell. A graph is plotted of 1 over I on the y-axis against R1 plus R2 on the x-axis. Okay, determine the expressions for the gradient and the y-intercept. Okay, so if we expand this equation, we get I R1 plus R2 plus I small r. Okay, so so we have uh, this equal to E. Okay, so now we bring it over here. Now we cross multiply I and E on both sides, so we have 1 over I. Actually, we could have done that over here also. Uh, okay, let's do this again. Sorry, my bad. When we cross multiply, we get 1 over I equals to R1 plus R2 over E plus R over E. Because we just need these two, combined. So as we can see, the gradient can be described by 1 over E R1 plus R2 plus R over E. Right. So 1 over E is our gradient and R over E is our y-intercept. Okay, values of R1, R2, and I are given in the table 1, 1. Each resistance value has a percentage uncertainty of plus minus 5%. Okay, now when we see this, whenever we have to add two quantities and their resistance, their uncertainty is given in percent, we need to, for the uncertainty, we will have to multiply by 5% plus 5% of this. So basically it will be 5% of the sum actually. So it will be, so the uncertainty in the sum of R will be actually 5% of R1 and R2. All right. So we have 22, 47, and 56. Okay. So 22 plus 33, we have 55. Then 22 plus 47, 69. Then we have 56, 78. Then we have 30, oh sorry. Then we have 33 plus 47, we have 80. Then we have 33 plus 56, 89. And then we have 47 plus 56, 103. Okay, now we need the 5% on each of them. So 5%, oh sorry, no, multiplied by 55, that is 2.75. First I will write it and then we will deal with this. Okay, no, we can actually do this over here. This is just going to be 3. Okay, then we have 69. 3.45, this is plus minus 3. Okay, then we have 78. 3.9 plus minus 4. 84. Then we have 89. 4.45, still roughly 4. And then 103. Sorry. We get 5.15, so plus minus 5. Right. Okay. Now we need the reciprocals of amperes. So 1 divided by 17.2, sorry, 17.2, 0.058, 14.2, we have 0.070. Wait, hold on. Let's go into the graph and see. Wait. Oh, this is in amperes. Okay. So this is in milliamps. When we convert it, this is this, and we need, so we have to convert it into amps basically. So 1 amp is basically 1000 milliamp, right? So 1 milliamp is actually equal to 10 raised to power minus 3 amperes, basically, right? So this is actually, you can say, 17.2. I didn't realize this. 10 raised to power minus 3. Actually, all of these values, as you can see, they will be multiplied by 1000. So this is 58.1. Wait, again, let's see the resolution on this. So we have 1, 2, 3, 4, 5. This is 92, 91, 92. So 90.5, 91, 91.5, 92. Okay, so we have 0.05 resolution basically. Okay, so 2 decimal places, it's fine if you want to use them. So this is 58.14. Then we have 14.2, 70.4, 2. Then we have 12.8, 78.13. Then we have 12.4, 80.65. Then we have 11.4, 87.72. Okay. Then we have 10.1. Sorry, 10.1. We get 99. Okay, right. Right. Calculate and record the values of R1 and R2, 1 over I, include the absolute uncertainties. Okay. Plot a graph of 1 over I per ampere against R1 plus R2. Include the error bars for the R1 plus R2. Okay. All right. Okay. So I'm gonna sketch this and then I'll come back. Okay. So we are back. We have drawn the 2 lines. Worst fit is the steepest, best fit is as the name already suggests. We have also marked 2 points each that were clear on this. Like I'm working on the screen, so the points look bigger, but the condition is that they have to be less than half of a group square. So you can use a little bit sharper pencil to make slightly better points over here. Okay, so first order of business, we need to find out the gradient and the uncertainty of the gradient. Okay, so first off, we need the best fit gradient. And we also need the worst fit gradient. Okay, so for the best fit gradient, we have points 107.5, so the y values I'm noting, 107.5 and 62.5. triple one and 60. Okay. Okay. For the worst fit, we have 107.5 and 60, 60. Okay, all right. So 107.5, 107. Okay. So 107.5 minus 60, and then 107 minus 60. Okay, so let's find out this. So 107.5 minus 62.5 divided by triple one minus 60, that is 0.882. And then we have 107.5 minus 60 divided by 107 minus 60. So it's very close to 1.011. Okay, so now the uncertainty in the gradient is going to be, the absolute difference of these, 1.0011 minus 0.882. So 1.011 minus 0.882, this is 0.129. So approximately equal to 0.1. So 0.1 is our absolute uncertainty, and to one decimal place we will choose, one decimal place we will choose our gradient to 0.9. Right. Obviously, this value cannot be having more decimal places or more significant figures than this. So you could make it like 0.10 and add 88 over here. For example, you could make it like 0.88 plus minus 0.10. But this is going to be an overkill, but definitely you can do it. Okay, all right. Now comes the y-intercept. For the y-intercept, we need the best fit and the worst fit. Okay, so C is equal to y minus mx. C is equal to y minus mx. Y, let's take one of the values. This is the best fit. So let's take either one of them. So 62.5. 62.5 minus 0.9 times by this thing. Oh, let's take, you can take 0.88 also, that's fine. 0.9 times by 60. And for the worst fit, let's take 60 minus, that was 1.011. Actually, let's take the slightly better ones, 0.88, 2 decimal places, and 1.01. Let's take 0.88 over here. It doesn't really matter. Over here, we can use that 60. Even the 0.91 is fine. That's fine. So 62.5 minus 0.9. Let me show you what the difference is. Times by 60. If you choose the 0.9, it's going to be this. If you choose 88, is going to be 9.7. So 8.5 to 9.7. That's not quite a lot of difference. It's again up to you. Let's use the 0.9 since we already wrote it. So that's the 8.5. Okay. All right. Next up is the 1.01. So 60 minus 1.01 times by 60. We get minus 0.6. So the absolute difference between these, so 8, so absolute 8.5 minus this value is 9.1, or just simply 9. So best fit, y-intercept, 8.5 plus minus 9.0. Alternatively, you could also write, 9.0 plus minus 9. This would also be, roughly fine. But you let's stick to what we actually found over here. Okay, using your answers to A, C3, and C4, determine the values of E and R, include appropriate units. Okay, so for the values of E and R, okay, so going back to the E and R. E and R. Where were the E and R? Yes, okay, so 1 over E was the gradient, y-intercept was R over E. Okay, so gradient was equal to 1 over E, and y-intercept was equal to small r over E. So gradient, we said that that was equal to 0, what did we find out to be? 0.88 or 0.9, let's choose 0.9. 0.9 equals to 1 over E, so E is going to be 1 divided by 0.9, that is 1.11, and this would be, let's choose 8.5, R over E, so R would be equal to 8.5 times by 1.11. This times by 8.5 gives us 9.44. So let's just keep it this way. So either you can write it as 9.44. No, sorry, opposite way. 1.11, or you can write like 1.19.4. It's up to you. Uh, oh, the units. E was the EMF, right? So E is the volts. R is in ohms. Okay, determine the absolute uncertainty in E. Okay, so E, since it is, the reciprocal of the gradient, it has the same uncertainty as this. So absolute uncertainty in E is basically the absolute uncertainty in gradient. So that was 0 point plus minus 0 0.1. Right, okay. The experiment is repeated using the same cell. The value of R1 is 22 ohms. Determine the resistance R2. That would give a current of 7.5 ampere. So we had the equation somewhat like this: R plus, what was it? No, R1 plus R2, sorry, my bad. R1 plus R2 plus small r, okay. That's R2. Okay, so we need R2, right? So R2 would be E over I minus R1 minus R. So E was 1.11 over I is 7.5 milliamps minus 3, minus R1 is 22, small r is 9.44. That we have just found out. So 1.11 divided by 7.5 times by 1000 minus 22 minus 9.44. That comes out to be 116.56 or just simply 170 ohms. You could also round it up to 120 also. All right, so that's the end of this paper. See you in the next paper. Bye bye.